Okay, so here's what we are going to do today. Where did my page go? Okay, we are going to start section 10.2. We won't be able to finish it, but we will have some start. So remember that we have been studying curves given parametrically, and why are we interested in curves is pretty obvious. For example, if you view the curve as the path of a moving object, then you're going to use a third parameter like a t, which will so you can express the position of the object in terms of the time parameter, for example. So let's say I have a curve C here, and the curve C is given by x is x of t, y is y sub t, and time progresses from A to B, let's say. And then I have this green curve, that's the path of the moving object, let's say. And if you think about it, at any point, what's the direction of movement? Or what should be the direction of velocity at any point? Anyone knows what should be the direction of velocity at any given point on the path? Well, it should be tangential to the curve, right? So if at this point here, let's say this point here is x0, y0, and let's say this point is traced at time t0. And so if I want to know what's the direction of velocity at this point, then that's going to be given. The velocity would be tangent to the path. And so one quantity that people would be interested in is what's the slope of the tangent. So that's what we want to discuss today. What would be the slope of the tangent at that point? So how are we going to find the slope of the tangent at that point? There are a couple of ways of doing this, but this is the one that I have adopted here is the following. It's obvious the way I drew the curve, right? So the bug is, let's say, moving this way, and the entire curve does not represent y as a function of x, right? Is that clear? Why is that the case? Well, it doesn't satisfy the vertical line test here, right? The vertical line test is not satisfied on this portion. So the entire curve doesn't represent y as a function of x. However, I am trying to find, the slope is a local behavior. It's a local property. So all I care is what is happening near this point, right? So let's assume that there is a portion of the curve around the point where y is a function of x. Am I making sense? Everybody is okay with that? So I am assuming here, so the assumption that I am making here is that a small portion of the curve around the point x0, y0 represents y as a function of x. So I can view this portion as y as a function of x, okay? And in that case, if y is a function of x, then what's the slope? So we are basically saying that y is f of x, right? We are basically saying y is f of x. If y is f of x, then what's the slope at the point x0, y0? Slope would be given by what? The slope, you're right, the derivative, right? So the derivative of y with respect to x evaluated at x0, right? This quantity here, the x coordinate of the point is x0. So if I have y is a function of x, then the slope at x0 is given by the derivative of y, right, at x0. So the derivative of y with respect to x evaluated at x0 is the slope, right? The question is, how do I find that slope? So before we go there, notice that so I have to evaluate the derivative of y with respect to x at x0. However, x0 can be found by evaluating the function x at t0. Everybody's clear with that? So the question is, how do I find this quantity? If I find that, I can find the slope. Well, notice what I'm going to do is the following. X is a function of t, right? X is x of t. Y is a function of t as well. But I want to view y as a function of x as well. So think of this. Y is a function of t, and I can also view y as a function of t via x. So I can think of y of x of t. So what I'm saying is that y evaluated at x of t will be the same as y of t. You guys realize that? So I know that x and y are both functions of t. Now if I am viewing y as a function of x, then I will be able to express y of t as y evaluated at x of t. Am I making sense? Because we are assuming that y is some function of x. Y is some function of x. So y sub t would be the same as y of x of t. Now what is so good about it? Well, now I take the derivative of both sides with respect to t. If you take the derivative of y of t with respect to t, you just get dy dt. How about the derivative of this guy with respect to t? Well, I have a composition here, right? So chain rule is applied. If I apply the chain rule, what do I get? I get the derivative of the outside with respect to t, evaluated at the inside, multiplied by the derivative of the inside, right? So notice that I have the derivative of the outside with respect to x, and then evaluated at x of t, multiplied by dx dt. Everybody's clear on that? So that's chain rule. And from here, I can notice that I need to find this quantity here, right? The derivative of y with respect to x evaluated at this quantity, which something I can solve for that right here. So all I have to do is divide both sides by dx dt, and if I divide this guy by dx dt, then I get the derivative of y with respect to x evaluated at x of t. If everybody is clear on what I said. Any questions? Is this making sense? All right, so then in particular, I want to know what's the derivative at time t0. So in this equation that I have, all I have to do is replace t by t0, and that's going to give me the derivative of y with respect to x at the point x of t0, and that's going to be given by evaluating this guy at t0 as well. Now how about second derivative? Well, the second derivative is needed because maybe I need to know the concavity of the curve. So if I want to know something about the concavity of a curve, I could use the second derivative. So the question is, what's the second derivative of y with respect to x evaluated at x of t0? Remember, x of t0 is the point x0, right? And so what's this second derivative? Well, it's given by this formula here. Notice that in the denominator here is the same as the denominator in the previous line. But in the numerator here, I am taking the derivative with respect to t of what? I am taking whatever derivative I obtained here, that's what I'm putting right here. Is that making sense? So we obtained the derivative of x of t, derivative of y with respect to x evaluated at x of t. Okay? And that quantity goes right here. So whatever you found in star, that's what is coming here. So what I'm saying is this quantity that I have here, that is what's going right here. Right? That's going inside of this bracket. Everybody is okay with that? If you have questions, please go ahead and ask. So let me just recap for a second. We have a curve. X is x of t, y is y of t. I have the point x0, y0, and I'm assuming that x0, y0 is traced at the time t is t0. Okay, and I want to know what's the slope of the tangent at that point. And so notice that this is x0 right here, right? This is x0. So what we are assuming is that a small portion of the curve around x0, y0 will represent y as a function of x. So because y is a function of x, then I know that the slope is given by the derivative of y with respect to x evaluated at x0. So I know that the derivative is given by, right here, the slope is given by derivative of y with respect to x evaluated at x0. However, what is x0? x0 is basically the value of the function x at t0, right? That's the x coordinate at time t0. Now, my question is then, how do I compute this derivative? How do I compute this right-hand side? What we are saying then is, because I am viewing y as a function of x now, so imagine that you can express y in terms of a formula in x, right? So I know that I already have y as a formula in terms of t, right? Because the curve is y of t. So I have a formula for y in terms of t already. And because I am viewing y as a function of x, then I can say y evaluated at x of t is the same as y of t. Okay, right here. We are saying y evaluated at x of t is the same as y of t. Because what am I doing when I'm evaluating y of x of t? Right? I am just evaluating I'm expressing y in terms of t, right? So I'm assuming that I have a formula for y in terms of x, and then I'm replacing x by x of t. So I am expressing y in terms of t. Well, that should be the same as whatever is given in the question, y of t, right? So then, once I obtain this equation, I can take the derivative of both sides. So when I take the derivative of both sides here, the right-hand side is just the derivative of y with respect to t, that's clear. But the left-hand side, I am taking the derivative with respect to t of a composition of functions, right? Where the outside function is y, and the inside function is x of t. So basically, we are viewing this as y is a function of x, and then x is a function of t, right? So the composition, so I am taking the composition of these two functions, right? Right here. Well, by chain rule then, what would be the derivative? it will be the derivative of the outside. So it will be dy dx, but it has to be evaluated at the inside, multiplied by the derivative of the inside. So I have dy dx evaluated at the inside, multiplied by the derivative of the inside right here. And once I obtain that, I can simply solve for the derivative of y with respect to x evaluated at x of t, which would be the ratio of dy dt and dx dt. Now in this symbol dy dx x of t, make sure that you understand I'm not taking the derivative of x of t. I am taking the derivative of y with respect to x and then evaluating the derivative at x of t. Right? I am evaluating dy dx at x of t. Okay? Notice that the reason we had to do all this because we don't have a formula for y in terms of x, right? If I have a formula for y in terms of x, then I could just take the derivative pretty easily. But so we are going to use this formula to find dy dx at x of t, and I'm going to give you an example in a bit that's going to make it clear. And so I have this formula that the derivative of y with respect to x evaluated at x of t0 is given by the ratio dy dt dx dt evaluated at t0. And the second derivative is given by this formula here, where the second derivative of y with respect to x evaluated at x of t0, that's given by the formula of the fraction on the right. You take the derivative with respect to t of the first derivative that you obtained. Is the derivative of the first derivative that you obtained up here, right? And then you divide by dx dt again, and then you have to evaluate the whole expression at t0. Everybody is okay with that? I guess if I do an example, that's going to make it clear. Were you guys able to write it down? So let's look at an example now. Instead of seeing this abstractly. Now before I give you an example, there are a couple of things we need to realize here. One is notice that there are a couple of possibilities here. One is I might have a curve like this, and then at this point there is only one tangent line, right? There is only one tangent line. But maybe I have a curve, say, like this, right? So what happens is that maybe the object is moving in this way and moving up like this and then coming down and going out like this, right? So it crosses the point here at two distinct times, right? It passes through that point at two different times. So let's say at time t1, it is at time t1 the tangent line is, this is at time t1, that's the tangent line, right? And then at time t2 the tangent line would be the other one, right? So for a curve at the same point I might have two different tangents, right? That's because the object is moving through the point at two different times. Okay, at two different times with in two different directions. Everybody is clear? And there might be another case, which is that the curve looks like this. It has a sharp point like this. What happens in that case is that there is no tangent at that point. Okay, we say that we have a if we have a situation like this, then we say that there is no tangent there. Because why is that? The idea of tangent is that if I pick a really small portion around this point here, right, very small portion, no matter how small you pick, you'll always have points on the two other sides like this, which is going to make a triangle. So you will never have these 3 points lying on a straight line approximately. Am I making sense? That's the intuition, that there is no tangent there. Okay, so we are not going to worry too much about this situation here. So let's look at an example. Let's say the following example. So here's my example. Let's say I have the curve C, and for this curve, x is given to be t squared, and y is given to be t cubed minus 3t, and t could be any real number. Okay, t could be any real number. All right, so the first question that I want to ask is let's say I want to find the intercepts, that is where the curve crosses the x-axis and the y-axis. So let's say I want to find the intercepts. So I need to find then the x-intercept. Let's say I want to find the x-intercept first. X-intercept. How would I find x-intercept? Can anyone tell me how I can find the x-intercept? Y equals to 0, right? So let's set y to be 0 and solve for that. So if y is 0, then we obtain t cubed minus 3t is 0. If I factor out, I get t times let me see for a second. Yes, t times t squared minus 3 equals to 0. So either t is 0, right? T is 0, or t squared minus 3 is 0, which means t is 0 or t is what? Plus or minus root of 3. Okay, so I see that for those values of t, the object is touching the x-axis. Okay, so let's now well, we can figure out the corresponding values of the x and y coordinates, right? So what are the points? So what are the intercepts? The x-intercepts are, well, when t is 0, what is the value of x? When t is 0, what's the value of x? 0. And what's the value of y? 0 as well, right? When t is positive root 3, when t is positive root 3, what is x? X is 3, right? And y is obviously 0 because it's the x-intercept. And then when you plug in negative root 3, you get 3, 0 again, right? So that means this point is traced at 2 different times, right? So this point is traced at 2 distinct values of t, which is plus or minus root 3, right? Which is plus or minus root 3. So we found the x-intercept. How about the y-intercepts? Yeah, so y-intercept, I have to solve x equals to 0, which tells me that t squared has to be 0 because x is t squared, right? And so that tells me t is what? T is 0, and we know that for t equals to 0, the only point I get is 0, 0, right? So that's the y-intercept as well, because that's the only point where the curve touches the y-axis. So that's the only y-intercept. Okay, so that was question 1. Okay, what is question 2? Let's say I want to find the points where the tangent lines are horizontal. So first of all, let's just find, well, you know what? My second question is the following. Let's say I want to find the equation of the tangent lines at the x-intercepts. How can I find that? Remember, the x-intercepts are those 0, 0, 3, 0, and 3, 0, right? Let me just say, for now, at the x-intercept 3, 0, just 3, 0. So let's just cross the S. At this point, how do I find the equation of the tangent line? I know there are two, right? We know there are two of them. I need to find the slopes, right? I should have signed out, okay? Okay, so how do I find the slopes? Well, the slope is given by what? The slope is given by, we know that it's given by, yeah, so what was the formula for the, so it's given by dy dx, and I have to evaluate it at what time? At x of what time? We know that the point 3, 0 is obtained at what time? Plus or minus root 3, right? So I'm going to get two different slopes. What's that? Well, I mean, it's not necessarily time, but I'm just using time. But if you have negative time, it simply means past. Okay? So I need to find the slope of the two tangents at this point. So if I plug in that, my formula says this is dy dt, dy dt divided by dx dt. And then after I find this ratio, I have to evaluate the ratio at plus or minus root 3, right? So then, what is this quantity? Well, what is dy dt? You guys have the y function, right? What is dy dt? 3t squared minus what? 3. And what is dx dt? Because it's t squared. So I have to evaluate this at plus or minus root 3. And what do I get? If I plug in plus or minus root 3, what is the numerator? Is the numerator just 6, no matter plus or minus? You guys agree with that? The numerator would be 6. What's the denominator? Denominator would be plus or minus 2 root 3, right? Right? And then you can cancel out 2 and a 6, so you get plus or minus. You guys agree that I get just root 3? Because 2 and a 6 cancels out to 3, so you get 3 divided by root 3, and then that's just root 3, right? You guys agree with that? Right, so that's the slope. So I have found the slope. Now, remember, we are trying to find the equation of the tangent at the point 3, 0, right? At the point 3, 0. So how do I find the equation of the line going through that point, having slope given by these numbers? So I'm trying to find two different equations, right? Two different tangents. So what's the point intercept formula? I mean slope intercept formula. Or I should say point slope formula, not yeah, it's y minus. So what is y value here? The point, it goes through the point 3, 0, right? So it'll be y minus 0 is equal to the slope. Slope is positive root 3, let's say, and then x minus 3. That's one. That would be one of the tangents. The other tangent would be what? With a negative slope, x minus 3. And this is the tangent at what time? This is the tangent at time. Root of 3 was the time actually. The slope, it was the same as the time. And this is negative root 3. So at time negative root 3, I get the equation of the tangent given by the second one, and at time positive root 3, the equation of the tangent is given by the first equation. Everybody, let me take a second here. Everybody's feeling okay with this? Questions? So remember, we plugged in this time, right? This time is what we plugged in. So for two different times, I get two different slopes. All right, so that's just finding equation of a tangent at a given point. Another part of the question would be, let's say I want to find the points where the tangent lines are horizontal, right? Where the tangent lines are horizontal. How would I find that? Anyone? Yeah, so you want to find the points where the derivative would be 0, right? So remember what was the derivative? The derivative of y with respect to x evaluated at x of t, that was given to be, we looked at dy dt, right? Dy dt divided by dx dt, and then we found that to be what? I think 3t squared minus 3 divided by t squared, right? Oh, so 2t divided by 2t. Now the question is, we want to find tangents, horizontal tangents, right? Well, horizontal tangents means they have slopes 0. So you want the slope to be 0. That means you want to solve the derivative to be 0. So that means you want to find values of t for which the derivative is, oh, this is 3t squared minus 3 over 2t equals to 0. If a fraction is 0, doesn't that mean that the numerator is 0? So that means I have this, and then I could say t squared minus a 1 is 0 because I can divide both sides by 3, and then t is clearly what? Plus or minus 1. So at those two times, whatever points are traced, at those points I have horizontal tangents. So what are the corresponding points? So when t is negative 1, what's the value of x? You guys have the formulas for x and y. X would be 1, right? And then y is what? Y is t cubed minus 3t, right? Negative 2. And then when t is 1, then x value is still 1. And then this time, what is the y value? Again, t cubed minus 3t. So if you plug in 1, did we make a mistake? This one is what? This one is positive 2, right? This one is positive. This one would be negative 2, right? Or is it the opposite? Say it again. Okay, what is y? Y was t cubed minus 3t, isn't it? So when t is 1, you get 1 minus a 3. That's negative 1, negative 2, right? So that's fine. And then when t is negative 1, then you get negative 1, positive 3, right? So that's 2. So we are okay. We are okay there. All right. So these are the. So I get these 2 points, right? One is this, the other one is this. At these 2 points, the tangents are horizontal. Okay. So that was 3. How about finding points? So find points where tangents are vertical. Well, once again, we know that the derivative of y with respect to x, I'm just going to ignore writing x of t and so on. We got this to be 3t squared minus a 3 over 2t, right? And because it's a rational function from Calc 1, we know that the vertical tangents occur when the denominator of the derivative is what? So the vertical tangent occurs when t is 0. So we have a vertical tangent at t equals to 0, which means in that case, what is the x and y? X and y was 0, 0, right? 0, 0. Okay, so we know where the tangents are horizontal, the tangents are vertical. The next thing I want to do is, that was 4, right? Number 5, what I want to do is figure out the behavior of x and y. Where x is increasing and where y is increasing, decreasing. So let's make a real number. Remember, t was from negative infinity to positive infinity, right? Where is the derivative of x 0? The derivative of x with respect to t, right? The derivative of x with respect to t was what? 2t, right? And 2t is 0 when t is what? 0. Now I want to know what's the sign of x prime on the left of 0? Negative. On the right? Positive. So I could say that x is decreasing here, increasing here, right? What's the value of x here? We know that the value of x at time 0 is 0, right? Now, I also need to know I know that x is decreasing up to 0, right? On the left of 0, x is decreasing, but where is it decreasing from? Where is it decreasing from? That is, when t is big and negative, right? When t is big and negative, what is x? Is x big and negative? What can you say about x when t is negative and big? What's that? Well, x is t squared, right? It's big and positive, so I know that x is coming from positive infinity. What can I say on the right-hand side of 0? It's going back to infinity, right? And in fact, x is t squared, so x is like the parabola in terms of t. All right, so we want to do the same thing for y. Okay, for y, what can I, for y, what are the derivatives? What was the derivative of y prime? What was the derivative of y? 3t squared minus 3, right? And when is this 0? This is 0 when t squared minus 1 is 0, when t is plus or minus 1, right? So here's my 0, and here is negative 1, let's say, and here is positive 1. So now there are two places where the derivative is 0, right? Negative 1 and positive 1. So what's going on to the left of negative 1? Is y increasing or decreasing? Well, what's the sign of the derivative of y on the left of negative 1? Well, all you have to do is plug in negative 2 in the derivative of y, right? So what's the derivative of y? The derivative of y is given right here, right? So it's 3t squared minus 3. If you plug in negative 2 there, right, you get what? Positive. So I get it's positive here. And then if I plug in a number between negative 1 and 1, suitably 0, right? If I plug in 0, I get negative. So the derivative is negative here. If I plug in 2, I get 3 times 2 squared minus 3, so that's positive again. So for y, we know that it's increasing here up to this point, decreasing up to 1, and then increasing back. What's the value of y at negative 1? 0. And what's the value here? The y value at negative, when t is negative 1 or positive 1. Hey, wait a minute, what are you saying? It's not 0. It's not 0, right? When t is negative 1, the derivative is 0, but what's the value of the function y? At negative 1 it was 2, right? At 1 it was a negative 2, right? So it was negative 2. Okay, now is it coming, so y is increasing up to negative 1. Is it coming from negative infinity? How do I know that? Well, look at the function y, right? Y of t was t cubed minus 3t, right? So when t is big and negative, what is t cubed? Big and negative, and that dominates 3t. So I know that it's coming from negative infinity. And then, of course, then it decreases from 2 to negative 2, right? And then it increases back to what? Positive infinity, because when t is big, t cubed is big. So we know that where the functions are increasing and decreasing. Okay, I am out of time. But this is what I want you to do. Look at the second derivative, compute the second derivative, and then you can come up with the concavity. And then sketch the curve. Okay, sketch the curve after that.
I'll wait for my Yeah.